lecture on mapping the Calogero model to anyons.
Today I would like to present some work that has to do with an explicit mapping of the Calogero system to two-dimensional anyons. That's work done with Stéphane Ouvry, who is from the Laboratory of Statistical Physics, etc., from Orsay in France, and it's a recent preprint to appear. Actually, in this talk, I will try to answer a very fundamental question. Aren't you sick of me yet? This is my 5th talk. Do you still want me to keep talking? I mean, I'm sick myself being up here, quite frankly. And for that matter, didn't you have enough Calogero yet? Well, be that as it may, I will give this talk, and I will try to build it upon 2 very important principles. The first is never underestimate the pleasure of the audience listening to what they already know. So if you hear stuff that you have heard before or you knew before, that's fine. Please indulge me. And the second principle is that nobody ever hated a speaker for finishing early. So I will try to earn your love today in this particular way. Yes. Although, I was about to say, although I might fail. Right. Anyway, let's go on to the real talk. So, we know very well that generalized quantum statistics do exist in 2 and 1 dimensions. In 2 dimensions, it's the famous anyons introduced by Lenos and Murheim several decades ago, and then kind of expanded and used for practical, real systems by Wilczek and other people. And the canonical manifestation of those anyons is, of course, in the quantum Hall effect. In the fractional quantum Hall effect, excitations obey anyon statistics in the proper sense of two-dimensional statistics. On the other hand, I try to persuade you that in 1 dimension, you can also have a concept of statistics, one that involves a dimensionless parameter, not other concepts of statistics that have been introduced. And that concept of statistics is basically realized by Calogero particles. The interaction endows them with that kind of statistical property that manifests in their scattering, which is kind of the analog of an exchange in 1 dimension, as well as in their quantum statistical mechanical properties. There are several indications that there are relations between these models. First of all, fractional here, fractional there. Maybe there is some connection. There is some suggestive similarity of the Calogero wave functions, energy eigenstates, and the anyon wave functions in the lowest Landau level. What that means in practice means that they both exhibit this kind of Jastrow function, this kind of van der Monde determinant with fractional power. The correspondence is that the real 1-dimensional coordinates for Calogero particles become mapped or become analogous to the complex coordinate of anyons on the plane. And in fact, there already exist some results in this direction. One is kind of formal and has to do with alternative realizations of operators in the 2 systems. That's work by Brink, Hanson, and Konstein and Vasiliev, building upon the exchange operator formulation. And some more recent work on the matrix model non-commutative realization of fractional quantum Hall states. Work that was actually initiated by Lenny Susskind, and then in the particular fashion that realized as a finite system by myself. So yes, we do have some results, but both of these results are not kind of so direct. One is formal, and the other tells you here is another alternative system that has all the physical properties of the fractional quantum Hall state, but there is no one-to-one correspondence between the states. We would really like an explicit mapping rather than a formal one. Why would I like such a mapping? Well, there are several things. First of all, for some people, this would be intrinsically interesting. The real reason is that if you do have such a mapping and you're interested in calculate quantities in either system, then either you can do one calculation and get 2 things, or better yet, you can do it in one particular context, which is easier, and then try to export it to the other And again, the density-density correlations would be the canonical example. Also, because both systems exhibit some kind of particle-whole duality, it would be interesting to see how that duality maps between the two systems. This is something that I didn't cover in my review lectures. So, in the sequel, we will derive actually an explicit mapping between energy against states on either side. That will come in the form of an n-body kernel that, convoluted upon the states of one, will give you the other. Now, in case you are wondering, which you're not, I'm sure, but in case you are wondering, how can a two-dimensional system map to a one-dimensional system? Well, it's the well-known phase space reduction. When you have particles to the lowest Landau level, coordinate space becomes effectively phase space, and therefore the system reduces to one dimensions, and that's when you can have this mapping. So let's talk about the lowest Landau anyon model. Very briefly, just to remind you, we are talking about non-relativistic anyons of unit mass and unit charge to make our life easy. The anyonic statistical parameter is alpha, and that means that when you exchange the particles in the counterclockwise positive sense, their wave function picks up this phase. They can also That statistical interaction can also be modeled with the particles carrying flux tubes and interacting through the long-range Aharonov-Bohm potential of those tubes. I will consider that this system is in an external magnetic field B equal to omega c. So omega c is half the cyclotron frequency, so that I can talk about lowest Landau levels. And also consider that I have a weak confining isotropic rotational symmetric harmonic trap of frequency omega 0. What I mean by weak, I don't mean that there will be some approximations that will be done with omega 0 small. What I mean is that the lowest Landau level states will be considered to be the ground state manifold, because in principle what happens is that when you have a single particle in a magnetic field and an external harmonic potential, the flat Landau levels become now curved like that, so the states are like that, and the first Landau level becomes like that. And this curvature has to do with the external potential. So you see that at some point, the lowest Landau level will exceed in energy the first Landau level. Here, I would like to restrict myself entirely to the lowest Landau level, so just to make the energetics more plausible, I will assume that this curvature is small, but it will not affect anything else. You can solve this problem in two gauges. One is the gauge in which they do carry these flux tubes and they interact with the Aharonov-Bohm statistical potential, in which case their wave function is perfectly single-valued, and you can it will be bosonic. But the other one is the singular gauge, in which you gauge away that potential, and the price you pay is that now the wave functions are not single-valued, they have a holonomy, and you have to take that into account when you solve the problem. But the advantage is that if the Hamiltonian for anyons in that case, it assumes what I call the free form, the non-interactive form, is simply the sum of n Hamiltonians for each particle, magnetic field, external potential. And this is a combined effect of magnetic field and external potential, which is this term. Because our wave function has a holonomy, we will redefine it with this analytic factor times the rest. And to make our life even simpler, we also extract this harmonic Gaussian factor that we know will solve the harmonic oscillator problem in terms of the long-range behavior of the wave function. And we can define our Hamiltonian H as acting on psi, and it assumes this form. It's written in complex coordinates. I should have mentioned that. It's the standard Laplacian. And these three are terms that you pick because of the anyon statistics, this prefactor, and the fact that we have magnetic field and harmonic trap. This is still a problem that cannot be solved explicitly, analytically, even for a single particle. The problem is this factor. If you notice, both the Laplacian and this factor take the degree in z and z bar of the wave function psi and decrease it by 2. Everything else is basically fine. It keeps the degree as it is. And these are simply constants. So you could try polynomials, but the problem is that this combination here, when it acts on polynomials, it may not produce polynomials. It may produce functions that have singularities. So you cannot assume, and it's not true, that all your states will be of the polynomial type in Z and Z bar, which is the case for trivial statistics. But there is a subset of states for which this operator acting, a subset of polynomial states, for which this operator acting upon them does give you a polynomial state. For these states, you can solve the eigenvalue equation analytically. These are called the linear states, because then the energy will depend linearly on the statistical parameter. It's an interesting subset of the full set, but it's not the whole thing. But for our purposes, this is enough, because we're interested in the lowest Landau level, and the defining property of the feature of the lowest Landau level is that modulo this Gaussian factor that we pulled out, lowest Landau states are analytic in Zi. That means that both the kinetic term and that annoying extra statistical term drop out, and you can simply read off the energy. The normalized one-body eigenstates are simply powers of Z, and the many-body lowest Landau eigenstates will be products of those, but remember that this state psi has to be bosonic, because, sorry, this state psi is what multiplies these two factors, has to be bosonic. This takes care of the statistics, and this is just an extra factor. And therefore, in general, you have to sum overall permutations of such monomials. So this is the most general state that you can write. And the spectrum, which you read off, has this form. I wrote it in this way, first of all, because it's correct, but I pulled out this, and I paid the price of introducing this here, because what appears now here should remind you a lot of the eigenvalues of the energy of the Calogero model. These L's would be like the excitations, and this is the standard shift that you have to the ground state of a Calogero model, where alpha is L, our Calogero coupling constant, and n is the number of particles. If only you interpret this prefactor here as the strength of the harmonic oscillator potential, the frequency of the harmonic oscillator potential of the Calogero model. So this is our anyons. Jump to the Calogero model. Because that spectrum was similar to that Calogero model, we simply we remind ourselves of the Hamiltonian of the harmonic Calogero model. This omega now is this difference, and the L in this model will be the same as alpha. And we will seek a mapping between the anyon system and that system, in the sense that we want to have a mapping that will produce the energy eigenstates of anyons from the energy eigenstates of Calogero. There should be an F here. And from now on, we will set omega equal 1 to make our life even simpler. All these are choices of units. Now, for the Calogero model, we know, of course, the ground state. I have shown you before that it has exactly this Jastrow type. And note that now I'm shifting from L to G. The reason is that I'm using this Li for excitations. I'm stuck with them, and I don't want to confuse with L. So what was L here became G. And this is the standard harmonic factor. So this is the ground state, and I will write it in this way. Delta will always be the Vandermonde of the corresponding variables. And whenever you see brackets, it means sum over all particles. This way I will save myself some trouble in presenting formulas.
So Alexios,
yes.
So what was the filling? Do you have any notion of filling in the Landau level case?
I'm not interested, although I could. The filled Landau level would be the ground state, in which case, let's go there, in which case you choose all these L's to 0. The non-trivial filling factor comes from here. So if you choose all these L's to 0, this is 1, and therefore you just have the harmonic times the Vandermonde, and as you know, that gives you a fractional filling factor. That's what happens when all the anyons are gathered together near the origin. But I'm actually interested in all excitations of that state. Mm-hmm. Okay? So I will have a state where several particles have left the ground state.
The n in your Calogero is what? So
the what?
The n body n in your Calogero is what here? Is it it's a number of Calogero?
The n.
Yeah.
It's the number of particles, the number of anyons or the number of Calogero particles. You can take it to be large, but it doesn't have to be. Mm-hmm. So this is what we will try to do. to make a mapping between the Calogero eigenstates and the anyon ones. Now, this talk will be a little bit technical. I'll do my best to be brief and not to give you every technical detail. But when you set out to prove such an explicit mapping, that's what you have to do. So the real physics is in the introduction, what I showed you, and then at the end when I comment a little bit. But I would like to show you some of the meat in doing that calculation. You realize that the anyon states are explicitly known in the lowest Landau level, and I shouldn't say trivial, but easy to write. It's just monomials in Z times these prefactors. What is not easy is the Calogero eigenstates. Of course, they are known, but their form is not explicit and easy to write. And certainly, we don't have a mapping. So part of our trouble will be in establishing this correspondence will be to find a form of these Calogero states that can then be manipulated. For that, you use the ladder operator. I talked about it in my lectures. You simply define these ladder operators, AI dagger and AI, that are, this capital pi is what I wrote as a lowercase pi in my lectures. And it's exactly the same thing, but without the I. So this is an anti-Hermitian operator, just to save myself writing I's and confusing them with particle indices. There are no I's in this talk. And the nice thing about these pi's is that they commute. Those do not commute, but they satisfy a relatively simple commutation relation. And the bottom line is that you can create all the excited states by acting with such ladder operators, actually symmetrized expressions of ladder operators because you want a bosonic state on the ground state. So this is the form of the Calogero eigenstates. And you already realize that these L's that I have here will have to map to these L's that I have there, and that these Zi's that I have here will have to map to the Xi's that I have here. But the rest has to be figured out. So I will be looking for an n-body kernel that I will write KG of X and Z. They start for the collection of two n variables Xi and Zi, such that when you take this kernel and you multiply with the Calogero wave function and integrate, you get the anyon wave function, with the dynamical part, the part that depends on energy, and the important van der Monde-Jastrow type, which has to do with their statistics and filling. In principle, yes, but we didn't do it because we were exhausted by the time that this finished. So we said, okay, let's leave that for another exercise. But in principle, yes. No. Good question. This integral is integral over all variables dx. This is an n-dimensional integral. And these functions are, generally speaking, well-defined and bosonic, but in fact, I will show you later that I will even restrict this integral to a fundamental wedge, x1 less than x2 less than x3, and using properties of the wave function, that will be enough. But this is actually an n-dimensional real integral. Of the what? The Barkman-Fock term? You will tell me later, after you see what this is. So, let's try to build this kernel. To build it, I will need some tools, and the basic tool here is the corresponding Calogero Hamiltonian for the scattering model. A visual tool in all this talk and the paper that we wrote is that whenever you see a flat bar, it means above something, it means a scattering Hamiltonian or operator. When you see a wavy bar, a tilde, it means the harmonic oscillator one, okay? And whenever you see a hat, it means the exchange operator one. Why hat? Exchange operator? I don't know. Just so that we have something else. So here is the bones of that construction. You consider the scattering Calogero Hamiltonian, and you define the scattering Calogero eigenstate. That is, the eigenstate where all the particles come in with some asymptotic momenta, and they scatter off with some other asymptotic momenta, which actually we know they have to be exactly the same, but fully permuted. K1, K2, K3 becomes Kn, Kn minus 1, because that's what happens when particles that are impenetrable scatter each other. This H will have this behavior, of course, when Xi goes to Xj. And asymptotically, it will become combination of scattered plane waves, and that's what I have written here. It is a symmetric combination of all possible, it is a combination of all possible permutations of scattering states. And here the momenta will be denoted by Z. Would be the asymptotic momenta, scattering momenta of the particles. But then after I have my formulas, I can happily analytically continue them to be complex numbers. And this state that I wrote here, this asymptotic state, is the corresponding scattering states with the proper phase shift. And remember that there is an e to the I pi g phase shift for every two-body scattering. So this C counts all the two-body permutations, all the two-body particle crossings that you need to create that permutation. And this prefactor is chosen for technical reasons so that the incident and fully scattered wave have symmetric phases. It's not very important. I claim, this is the main claim of this paper, that the appropriate kernel that will do the job will be exactly that scattering state times these other factors. That means that in this kernel, the scattering momenta that appear through this function become anyon coordinates. It's kind of like a duality. The momenta are dual to the coordinates x, and they become the complex coordinates of the anyons in which they map. As I said, the proof is rather long and technical, but I will not insist on the details. Just to show you the basic steps why it works. I will use these operators A dagger to create the Calogero eigenstates, but I will do a similarity transformation so that they acquire their free form pi I. After I do that, using hermeticity, or rather anti-hermeticity of pi I can turn them around in the integral and let them act on the scattering state. Because symmetric combinations of such pi i's, when they act on an eigenstate, on a scattering eigenstate, they reduce to the eigenvalues of the famous conserved quantities of the Calogero model. That will give me something simple. That will give me some factor. So that will be the biggest part of the job. But there is still another one remaining, that the remaining integral that you get has to reproduce this van der Monde determinant. And although you may say that this is the lesser part of this business, you want to reproduce the dynamical factors mostly, it turns out to be that it is most challenging one analytically. And in fact, we have only strictly proven it for integer g, for n greater than 2, for n equal 2, using known properties of functions, we could prove it generally. But this should be true in general by analytic continuation. But this is just wishful thinking, I should stress, okay? Okay, let's go through some steps of this proof. We write the creation operators in this form. If you conjugate the pi, the generalized momenta, with these exponential factors, you get AI. It's exactly the same as when you have three particles. Note that if I had done it the other way around with plus here and minus, I would have gotten the annihilation operators, but it's crucial that I have these ones. So I write the convolution integral, the one that I propose that will do the job. I substitute the form of k that I gave you before. It's this whole thing. And then I create my Calogero eigenstates by acting with this symmetric creation operator on the ground states. Using this property, I eliminate, by substituting these A daggers with respect to the pi's, I eliminate this and I double that exponential. But now I'm free to use hermeticity and apply pi here, and I do it. And when I do that, I claim, and I will not prove, but it is a standard from Calogero analysis, that these symmetrized products will actually produce the eigenvalues of the corresponding Calogero conserved quantities, which are exactly symmetrized products of powers of the asymptotic momenta. So everything works nicely. And you can look to lectures if you wish a proof for that step. So putting everything together, we have that this kernel acting on the Calogero eigenstate will produce this function, which is exactly what we want, some factors of z square, which are innocuous, times this integral, and now we need to show that this integral will reduce to, or will reproduce, the van der Monde factor for anyons. The only reason why I give steps in this proof is that because it introduces some tools that I did not tell you about in the pedagogical lectures that may be of interest. These are the so-called intertwining operators. So to use them, I have to move to the exchange Calogero Hamiltonians. Remember, hat means that you write the corresponding exchange Hamiltonian, and to know whether it is the harmonic or the scattering one is denoted by the index here. If I put a pi, it means it's the scattering one. If I put an A, like creation operator, it's a harmonic one. So I define those two Hamiltonians. These are not my Hamiltonians, but I define them as tools. And also I define the intertwining operators, which are simply the van der Monde determinants of the operators pi or the creation operators A dagger. And these were tools that were introduced by Felder and Veselov. I will show you what these do for you. Of course, because the A daggers and the pi's are related with this similarity transformation, the same is true for those intertwining operators. And another important property is that when you take these exchange intertwining operators and act on fully bosonic states, they reduce to some corresponding operators. These are not written easily in any explicit form in terms of determinant, but they reduce to some operators delta tilde for the harmonic and delta flat for the scattering that involve no exchange operators anymore. Everything has acted on B and has become plus one. But these new operators will now contain simply coordinates and derivatives. So I have three kinds of intertwiners. Why is this interesting? Because this is a tool to generate scattering states. The basic observation is that if you act, let's start on the lower, if you act with the exchange Calogero Hamiltonian on a fermionic state, you remember that the Hamiltonian has a term L times L minus Mij over Xij square. And of course, when this acts on a bosonic state, this will become plus one. So we have minus one. And when it on a bosonic state, and when it acts on a fermionic state, it will have a minus one. So you end up with L times L minus one on bosons and L times L plus one on fermion states. You say, oh, that's not a big deal. It is not, but note that L times L plus one is L plus one times L plus one minus one. What do I mean? I mean that by doing that, you are writing essentially the same model, but you are writing the same model, but with the coupling constant L increased by one. And I should be writing G here because I'm writing G, but I'm stuck with L. So you see that these operators have the property that they act on a fermionic state. And when they act on a fermionic state, they act as, again, the same non-exchange Calogero Hamiltonians, but with G plus one coupling constant. Because the pi's commute, the exchange Calogero and the intertwiners commute, so this will tell you that there is nothing interesting there. But things do become interesting when you let this relation act on a bosonic state. So when I put a bosonic state here and here, what happens is that this delta hat acting on the bosonic state gives me a delta flat. It's the corresponding reduce operator. But now this state has become fermionic. Why? Because this delta intertwiner is fully antisymmetric. It's a product of operators that when you exchange two particles becomes fully antisymmetric. And therefore, when H hat, the exchange Hamiltonian, acts on this fermionic state, it gives you the non-exchange Hamiltonian with G plus one. On the right-hand side, something similar happens, but now H hat acts on G first, so it gives you the flat Hamiltonian for G, and then that operator, this remains a bosonic state, gives you delta flat of G. So, because this is true, of course, only on bosonic states, but from standard locality arguments, you argue that if this is true for bosonic states, it must be true in general. So you get this operator relation that if you take delta from the left to the right of the Hamiltonian, this non-exchange delta intertwiner from the left to the right of the Hamiltonian, it lives behind a Hamiltonian with a different coupling constant. So you can use this iteratively, and you say that you can start from H0, the Hamiltonian for zero coupling constant, which is the free bosons, and act with a sequence of such intertwiners, and those will go through and will leave you behind the Calogero Hamiltonian for strength G. That's nice, but it only works for integer G, and that's where the technical requirement for integer G enters. Well, after you have that, you can take it and run with it. You can act on the symmetrized free plane wave. This is the bosonic scattering state, if you wish. That's how free bosons scatter. You just symmetrize over their plane waves. And by acting on them, you get this relation. You get the eigenstate of the Hamiltonian. The free Hamiltonian action on this is just 1/2 sum of the momenta squared. Fine. But now you have the task of finding how all these intertwiners apply on the symmetrized plane wave. But the point is that we can now express our intertwiner that needed this eigenstate, which is what we have just produced, in terms of that action. So that's, if you wish, an operator solution of the scattering Calogero model. Now here is another remarkable fact that is by no means obvious, and it was technically a little bit difficult to prove, that this scattering state is completely symmetric. It's kind of under exchange of the x's and the z's. Again, remember that the x's are the coordinates and z's are the scattering, asymptotic scattering momenta. There is no reason whatsoever why, if you exchange the two sets, this function should remain the same. And yet it is, and I refer you again to the paper for the proof. And we need that for another technical trick. If you know that this is what happens, you can take this expression and simply write it for z and x as opposed to x and z, because this is symmetric. It doesn't matter if you exchange x and z, but when you do that, this remains the same because it's already symmetric. But where you had operators here acting on x, now you have the corresponding operators acting on z. So you turned around your operators and they act on these coordinates z. And that's interesting, because that's useful rather, because now you can insert that in your integral of interest, because these operators act on z. They are invisible to the integration, so they can be pulled out. You can perform the integral analytically, and you end up with the task of finding out their action on that harmonic factor. So simpler, but still non-trivial. It remains to determine that action. This is where I gave up when I was writing the notes. I said, these guys will really hate me no matter how early I finish if I give them all the details. So you can do similar tricks that I did before. I refer you to the paper, and you discover that this sequence of operators acting on the ground state produce, lo and behold, the Vandermonde factor times this extra annoying numerical factor that is of no interest. Inserting that in the integral of interest gives you this, which is, of course, what you wanted to have. It tells you that if you take, actually, this is not quite what you wanted to have. This is part of your final integral, or this is part of your kernel integral. This was the residual integration that needed to be done. So I put it back to the integral, and this is my final result, that this kernel, which is written explicitly like that, acting on an eigenstate of the Calogero Hamiltonian, where this L stands for the collective excitations L1, L2, Ln of the Calogero state, reproduces exactly the corresponding lowest Landau level anyonic wave function with the proper filling factor, if you wish, and the proper excitation. So we have mapped Calogero particles to anyons. Okay, that was our designed mapping relation. Well, I'm doing well here, because this is my conclusions and outlook. You will love me for that, I'm sure. So, what I showed you today was an understandably and admittedly technical result that was nevertheless missing from the literature. It is an explicit mapping of Calogero to anyons. By the way, if you do that at the one particle level, it becomes the analog of some relations that you see in mathematical books about identities for the Hermite polynomials, etc. I don't know if that's part of what you were referring to. But such generalizations for Calogero, many-body Hermite polynomials, whatever you might want to call them, so they are many-body and they're not quite Hermite because they are deformed by the Calogero, were not known. So this is, if you wish, what we achieved here. This is the state-dependent part, the part that tells you that the dependence of this state on its quantum numbers, this energy quantum numbers, maps nicely, is established in full generality. But the fact that the Vandermonde determinant is also reproduced, we strictly proved it only for integer g. We strongly suspect that it nicely analytically continues for any value of g, if only because for n equal 2 we can prove it independently using some other identities. And if it works for n equal 2, it's not quite as good as if it works for 3, it works for n. But if it works for 2, it's analytic. We expect it to be analytic for n. There are, of course, open questions here to consider. One is, okay, why don't we do that now for the Sutherland model? Fine, we can do it, but we have to understand what it would map to. The Calogero model maps to anyons on the plane in a harmonic trap. The Sutherland model, which is particles on the circle, would map to what? One possibility, considered by people before, is that would map to anyons on a cylinder. So the non-compact momentum would be the length of the cylinder, and the non-compact momentum of the Calogero particles would correspond to the length of the cylinder, while the compact coordinates of the particles would correspond to the circumference of the cylinder. Another possibility is that maybe they map to anyons on the sphere. This is less intuitive, but there are signs that it may be the case, and that's an interesting problem. That's an elliptic, but when... Okay, so what about the elliptic model, which is the most general one? Of course, you could consider the hyperbolic, etc., but let's go straight to the elliptic. What would that correspond to? Again, there are some allusions that it may correspond to anyons on the torus, because one way to write the elliptic model is to compactify both coordinates and momenta. It's just that the momenta have to be compactified in a complex dimension. Of course, given the fact that we know so little about the Calogero elliptic model, and also anyons on a torus is another challenging problem. I don't know if much can be done here. And of course, the real question is, now that we have it, can we apply it to something interesting? And there we are open to ideas. That was it. Thank you.
I have comment and question. The comment is that when we worked on this Calogero and harmonic potential and we write it in self-dual form in terms of x's and z's, then we see some duality, which is in change of that U0 and U1. And it's very nicely in terms of tau functions, it's even simpler than that. Right. So this reminds a lot the story. We are not interested in the wave functions of the states, but this reminds. So maybe writing this in terms of those U's will be technically simplifying.
Let me respond to this comment and then you do the other one. You're absolutely right. It's tantalizing. Even use the same variables z because they are complex. There are two problems. First of all, I don't know how to establish that connection in practice. And second, that formulation is inherently classical, this dual.
We have quantum analogs of this.
We have quantum. Because here I'm explicitly working the quantum wave functions. So that's what I would like.
It works exactly the same way when it's operators.
If you have operators, that's great. I would like to see it.
Okay, and the question is, can you do something with this? For example, in quantum Hall effect, if you have this droplet, then you have some boundary states. So what would be the analog in Calogero?
Exactly. So this is the kind of questions that are next in the list. Of course, if you have a large n and kind of low energy boundary excitation, you don't excite the droplet all the way to a finite fraction of its depth, then this becomes the standard conformal particle theory. And this would work, and it's interesting as a check to see how it would work. The interesting thing would be to have large deviations from that state. So that's exactly the kind of question that, I'm sorry, corrections to the conformal theory, right? Two exactly interesting points that we want to do.
Any more comments, questions? Okay, if not, let's thank Alexios again.